Hello, this is a short video on cross-correlation, how it works and its application with respect to digital signal processing. Before we get into cross-correlation, a little recap on what correlation is. Correlation is the measure of similarity between two signals. Take these two signals, x and y, shown here. They are similar in shape between samples 0 and 2, with a peak lining up at sample 1 and a dip lining up at sample 2. But are less similar in subsequent samples, with a dip at sample 3 of signal x lining up with a rise in sample 3 of signal y. This can be confirmed by calculating the correlation. Correlation is calculated by individually multiplying the samples from both signals and then summing them together. Samples 0 from x and y multiply to 2. Sample 1 from both signals have a higher value and contribute more to the value of the correlation. Samples 2 are both negative, so they also contribute a positive value to the correlation. Samples 3 have opposite signs, and they contribute an overall negative value to the correlation. Subsequent values don't contribute anything to the correlation due to there being samples with a value of 0. The overall correlation value is negative, indicating that two signals are not similar. In fact, they're quite opposite. A large positive value indicates a strong correlation. A value of close to 0 indicates no correlation, and a strong negative value indicates the two signals are opposite to each other. The key takeaway from this is that to get the greatest value of correlation of the two signals, positive peaks and negative values have to line up. Now let's take a look at two signals that are more similar in shape. Let's replace signal y with signal z. It is clear just from looking at the graphs that the two signals are quite similar. Despite different values of the samples, the overall shape of the two signals is very similar. Calculating the product of each of the samples, it can be seen that the positive, negative, and 0 samples lining up leads to a greater positive correlation. The correlation is much higher, and thus signals x and z are more similar than signals x and y. It is worth noting that a larger correlation value might not always mean the signals are more similar, if the total energy of the signal is not taken into account. However, for the purpose of this video, this can be ignored. Now consider these two new signals, x and y. Anywhere the two signals do not overlap, the value of the missing samples can be considered to be 0. The peaks and valleys of both signals do not line up very well as is. Calculating the correlation as previously yields a positive value of 10. However, just from looking at the graph, it is clear that the signal y is much more similar in shape at samples 4 to 8 to signal x than it is at samples 0 to 4. Thus, we would expect the correlation to be much higher if signal y was delayed in time by 4 samples. This is where cross-correlation comes into play. Cross-correlation is essentially just correlation, but for every possible time shift of the signals that are being compared. Therefore, the output will be an array, with a value for each time shift as opposed to one single value. This paints a much better picture of if and where one signal shows up within another signal. It can be visualized by sliding one of the signals along the x-axis and getting the correlation at each point. Negative time shifts of signal y in this example yield a much lower correlation value. A time shift of 0 gives us the original value of 10 from just taking the correlation of the two signals. A time shift of 1 gives a negative value, as the peaks of signal y line up with the values of signal x and vice versa. A time shift of 2 yields a stronger correlation value than 0, as peaks and values in the two signals line up better. This pattern continues, and as hypothesized, we see the strongest correlation at a time shift of 4 samples in signal y. This indicates a strong presence of signal y in signal x at that point in time. Let's take a look at a more practical example of why this could be incredibly useful. In this demo, I have synthesized a signal containing a number of patterns with samples approximately equal to 1, -1, and 1. The aim of this demonstration is to use cross-correlation to find all occurrences of this pattern within the signal. This is achieved by cross-correlating the signal with an ideal version of the pattern 1, 1, and 1. I added noise to the signal to make it more realistic, as well as a few high and low samples to make it more challenging. Letting the simulation play, we can see a visual representation of how cross-correlation works, with the samples being compared highlighted in red. The bottom graph is the resulting values of cross-correlating the signals, plotted against the time shift of the signal pattern. At first glance, there is little to be seen in the cross-correlation graph. However, this changes when only the highest values are considered. I've chosen a threshold value of 90% of the highest value obtained for the cross-correlation. In an ideal world, all of the highest values would be the same. However, due to the presence of the noise, this is not the case. Highlighting all of the values over this threshold reveals all of the occurrences of the pattern. Cross-correlation is a powerful tool for identifying patterns in signals. I hope you gain some appreciation for its benefits in digital signal processing.